my first, sounds scary. My first experience like here in the US. And what I'm going to talk about, like it's something like templates for all seasons, like gravitational wave templates for all seasons. Like, and let's get started. Oh, okay. So I want to start with this. Like, these are some. You already seen like some of the. These are the spectrograms for gravitational waves. You have all the nice, very beautiful charts. Like, just I want things to keep in mind, like the duration of the signal, fraction of a second, except for like for binary neutron stars. I don't have to spend too much time on this. This is something that you already see. Like, but this is something that probably a few of you have seen, like maybe the type of parameters that I left here, like suggest the type of sources. This is like an Emory signal, like it contains like a stream isolation spiral signal, and it's still a signal that comes from a comparable binaries. Sorry, from astrophysical binaries, but for a completely different type of binaries. And look at the signal. These last months, if not years. And this is the type of sources, like stream isolation spiral or Emory's. They have like the primary, the more massive objects is at this mass here. It's a supermassive black hole. The smaller objects have this range of masses. Could be a stellar mass black hole or something more exotic. It could be also like a neutron star. And this is like these signals is very complex, and this is reflecting the type of orbits, very intricate. It's very different to what you have for comparable binaries, which is simply like circular orbits or on the plane with no eccentricity or inclination. And this is the main type of sources that I will talk about. And the sources are observed like on this interferometer here. The laser interferometer space antenna, LISA, or the like type of space interferometer, and they are in the bands of the millihertz, while LIGO sources are like here, around the hertz, and there is also type of source. This is the gravitational wave spectrum. This is one of the future like spaceborne observatory. Again, kind of very different like for what you have like for LIGO Virgo. LIGO Virgo, you know what you like, arms like, fixed like. These are like three spacecraft orbiting the Earth, like connected by laser, completely different things. That the type of for doing data analysis for this thing is much more complicated for what you have for LIGO Virgo. Unfortunately, I don't have time to go into the details of the data analysis. Just to give you an idea of a detector that we have for extreme isolation spirals. And these are things that is important, like solving the Einstein field equation is terribly difficult, very complicated. You have to solve like partial differential equations, coupled, and they are very way like to find the approximate solution for these equations. And you find that you have different approximation like this, like the complexity of the Einstein field equation. You have like numerical relativity. You solve them all mites of the Einstein field equation numerically, which is great, but it only works like for a certain type of binaries, which have like comparable mass binaries. If you go for higher, for sources which has more and smaller mass ratio, solving the Einstein field equation with the numerical relativity become extremely like expensive. We have other type of approximation where like weak field expansion, where the two sources are far away, they are slowly orbiting each other. There's like the type of scheme that I will discuss, which is like small mass ratio expansion or like perturbation theory. But this type of scheme of methods are not independent to each other. They talk to each other. I will show later how all of these type of methods are connected to each other. But to solve like the type of sources which I interest, like memories, big black hole, small like objects, we need to proceed like step by step. And this is like briefly the structure of the talk. I hope to cover like all of this, like probably we skip something like swing, but we first start with this kind of orbital motion, like geodesic motion and modification, no radiation reaction in this chapter. Then you add like radiation reaction, how we create the waveform. And when we go back circle, all the methods like used to model like extreme mass ratio binaries, as highly asymmetric binaries, can be used also for binaries that are not that extreme. Let's see if it works. Okay. Okay, let's see if I can make probably also. I don't know if you see like this type of cool like potential stuff. See? Ah, okay, let it go. This is like the type of orbits that, first of all, these are the equation of motion that you have for an object moving a point particle moving in space time. The motion is integrable. This is a miracle because we know about this. This is a hidden symmetry, something that it doesn't come like from the equation of it's a constant of the equation of motion, something that comes from like it's a hidden symmetry of the space time. This is a type of motion that you have. This is like a motion that covers the full like phase space. You have another type of motion here. This is like cool. This is like this one too. This is when you have resonances. If you pick your initial condition in the right way, your orbit will look like this. It doesn't cover all the parameter space, and you have this cool picture. Spin is called Misaju figure. Something that you can also produce while you have create an electric circuit and an oscilloscope. Like something like this type of thing. This is the type of motion that you have for geodesic motion. But what's happened? The small body spinning. After all astrophysical bodies like have a spin. Also, the pile of rock where we are standing like is spinning after all. Things get a little bit complicated. I don't want to get into the details and the lore of these equations. These are called the Matheson-Papapetrov-Dixon equation of motion. It's something that you take when you expand like your sources like in multiples, when you retain just point particle and dipole. Something that you do like in electromagnetism or Newtonian gravity, you have your potential, like you are very far from the sources like this there, and you are here, and you expand and you consider like the different. What I want just to say, all the things nice that you have like the geodesic motion, you have all sort of problem, motion of integrable, chaos, linear momentum and the angular momentum are no longer aligned. Even the norm or velocity is not conserved. It's a mess. Right? How do we solve like this type of thing? Well, as something that I learned that's problem in physics, something much smarter than me realized that you solve like even if you use symmetries or you use scales, like, or a combination of the two. If you don't have any of these two things, different scales or symmetries, well, we have both. And one thing like the spin of the small objects, like this, like the spin tensor, scale like as the mass ratio. And this quantity chi is like the specific spin, and I put here some values, and they are very, very misleading because you have like for the Earth, you have this value here. For a fast unknown pulsar, you have this value here. Say, oh, what the hell? Like it's just because you scale like in geometrize unit. Like, of course, the Earth like doesn't spin like fast as the pulsar, like the fastest one. This is just to say that for objects we have as a compact objects like neutron star, Kerr black hole, the parameter chi The specific spin is of order 1, so the entire light quantity here is of the order of the mass ratio. This is like exactly what you need like for extreme mass ratio spirals, and probably for also other type of sources with less extreme mass ratios. And then we have something even more important, like symmetries. The symmetry that save us, if you consider like curved space-time, you have the energy angular momentum, you consider as the energy angular momentum like we related to the two killing vectors. This is good. If you could fix like this center, this is a technical condition like this. You have to impose like some condition to fix the center of mass. You pick this. The secondary spin is also conserved. And then you have again the miracle out. Like I say, you have also two overlap constants of motion. The motion, what again, is interval. And then something that really, something recent that was realized, that is work like here by Geoffrey compare, with a small modular black hole, the motion is integral up to high order. Like we want to spend too much time here in the details, want to show you some cool picture, but at the end of the day, things simplify for the equation. You solve things perturbatively. Geodetic motion, the thing that I show like at the very beginning of the nice plot, perturbation due to the coupling to the small pin to the curvature, and you have that the spin tensor is parallel transported along the geodetic. This is like called the Mark tetrad, and allowed to write the spin vector here. This is like some nice results, some of them done by a person sitting in this table here. These are some of the results that you can have some of the small shift due to the spinning body for radial and polar motion. Need to be sure that the orbits are on track, and just change a little bit view. This is the type of orbits that you have. Total angular momentum, orbital angular momentum, a spin on the small ball. If you have two components, one which is parallel total angular momentum to the orbital angular momentum, one which is like perpendicular to the angular momentum. This is nice when you solve like your equation of second order, but your equation of motion that I showed at the very beginning for the geodesic are first order. And you can reduce like equation again in first order form. This was done like Wojciech Witrani implemented like in some recent work. This is all cool, but there is some problem. The motion is not separable now in theta. And your turning points are not constant. I will show this what does mean. And you have some freedom, which we can call like a spin gauge freedom, something fancy. It just means like you have some freedom, like to parameterize your motion. And this is some nice orbits. This is for Schwarzschild, where you have some analytic solution, which you consider like an orbit is Schwarzschild, but you solve it like on the equatorial plane. And then you do some inclination, and here you have just some cool plot. We have some effects here due to the component of the spin which is like not aligned. And this are spin flags. It's like geodesic motion here. You can see very nice here, like compared to my screen. Geodesic motion, perfect box, not deformed. Like when you have effects of a spin, you have like this. It's like having a box with a little bit squish, like, and you see like the box is like deformed. Right? This means that your turning points, even like by the edge of the box, are like not constant, like oscillating. Like you have all of these effects, and here. Like work that I done recently, I just pick like always shift to a constant of motion and pick it to 0, and this is when you fix the turning points. See the difference? Like here, squishy at the 4 box, still squishy, but this oscillation like average to 0. The size like is more or less the same. Also pick like quite large value of the mass ratio. All right, let's go to this part. Waveform from asymmetrical binaries. I don't want, again, to go too much. The main gist is like perturbation theory. We have to solve this piece here. How do we proceed? Well, physics, what usually do, like, you take your complicated equation, you find like a small parameter, you expand like in Taylor series, you hope for the best. And this is what you do. This is like a more sophisticated than that. You have like the background metric, and you have like this perturbation here. This is the motion is like push away from a geodetic motion, some modification. This is called the self force. Is like spin effect. If you want to know more, I recommend like this. It's enough to a faint of heart. Like there are a lot of technical details. Okay, now how much of this H, this method perturbation, do we need? Well, it turns out we need like these two, the first two. First order, second order. And this is because when you do like a 2 times scale expansion, this is like a classic work by Peter and Flanagan, that's more recent, some of the effects like scale different. Like this is like the more important thing is called adiabatic, your resonances, when you have all of these pesky correction here and the spin of a small body, or like conservative dissipative comes here. This is the picture when you have like a cleanest like binary, no environmental effects and so on, things become like more complicated. Environmental effects, probably some effects here, I guess. But that's considered like a clean binary, something like the simplest cases. Okay, if you have to remember something like this, like just look at the pretty colors. In the pretty colors, I say like, this is like 0 PA, blue, for visivity 1/4. Easy, easy. We can do like with no problem. It's been done like for decades. Relatively easy, like this is like, has been done most work recently. This is terribly hard. This is really, really hard. Like it's something like people has been banging their heads like for decades, and it's like this effects of the second order support and so on. The thing is, because some of these effects you obtain like by knowing information very away from the binary. You don't need to know the local information, what's happening inside the binary. Yeah, there are also other like simplification, but I want to show another things here. This is like, okay, so you need waveform. They need also waveform like we take like fast. How fast? Well, we need 1 year waveform in 1 milliseconds. So waveform like it's extremely long, complicated, intricate, you have to be generated extremely fast. Some people even argue that to be like even faster than this. How do you do that? There are different methods, different things. Like one of the problems that you have in more like your motion, you have all of these oscillations here, but you can like use like some techniques when you average your own motion here. This is done recently by Lisa for the spinning body, has been also worked by Phil, like in applying this the result. Finally, some waveforms. Here we are. This is like what's happened when you have like spinning, non-spinning, like purely like adiabatic effects, some spin effects. Very nice line. Then more and more. Look at the nice, beautiful like picturize all the structure, all the beatings here. This is like for spins, which are anti-alignment. So like this, or or just like this. There is no like spin possession. I have to not hurt myself. Here, you have some spin possession. This unfortunately is not evolving, it's just natural. It's like a work we have done recently with collaborators, and you see like the structure due to the possession of the spin body, and like something like this is much more complicated. Like, again, it looks like a pretty large mass ratio, but just to show that we can add also the spin of the possession with small more. Just to mention this, why it's terribly hard to compare like second orders and fourth order. The thing in red here, you have to solve perturbatively. You have this set of equation here, and some of the problem that you have by solving this, translating into this, you have singularities to remove, like it's computationally expensive, all that sort of technical details. But has been done quite some work in obtaining like results with Vartian space-time. It has been like the work that lasted like, I think it's fair to say decades, like to obtain like not I would say models, but it's a combination of like many years of work. So show also result for this is like for circular equatorial coordinates. This is the things that I want to show you. All of this like has been found for emeralds. Big body, small object orbiting around, mass ratio really small, and so on. These are the techniques. These techniques have been designed to solve this type of problem. Right? Some of these guys here, they try to say, all right, we have our nice waveform, which contains like all the correction that you need, like to model a binary for Lisa. What's happened if we put like the mass ratio like here? This would be inverse of epsilon. Q is really large, you consider M is Q really small, compare with plus minus. If they compare with NR simulation, we nicely overlap here, up near to the merger and ring down, but this is okay because the waveform that we have were not designed like to solve a comparable plus minus, just designed to solve the earlier part. And this leads me to the last chapter. How much time do I have? I'm going too fast or too slow? How much?
20 minutes.
20 minutes. Ah, I was too fast. But I will slow down here. Yeah, I also have like extra slide that I can use. Okay, this is like extreme waveform for not so extreme binaries. This is probably the part that may be more interesting for you. Okay, the motivation. Numerical relativity waveforms are the gold standard. If you want to model a comparable bus binary, you take your nice fancy model, you ask people like to do like the numerics, please tell me what numeric simulation you have. If your fancy model like doesn't compare well with the numerical relativity simulation, your model like can go out to the window. Like it's not. A numerical relativity simulation are very expensive. And other simulations are expensive to produce. They cover only a small fraction, a part, the non-changing part of the parameter space. If you only cover some where there is small mass ratio, spins align, the spin has to not be very large. And for the newest detector, we have like high signal to noise ratio, we will have longer signals, we will need probably high resolution, so computation even more expensive. What about eccentricity? Also, which eccentricity? Like, we are working with general relativity, like coordinates have no meaning. How do we find eccentricity? How do we add spin possession? And the idea like is to use some of the waveform, just backtrack. So a waveform produced like this in orange here, produced like with a perturbation theory method, into using it to cover some of the parameter space. But what we are missing, well, we're missing this part. But all of this part, people are very good at modeling this part, self force and perturbation theory. How do we have this? Well, we go for considering different scales. Let's go for circular orbits. We have like different scales. The spiral, 1 over epsilon, which means that the spiral like is very, very long. It's often very slow. Like the orbits vary very, very quickly, but the effects to the radiation reaction happen very, very slow. Then you go here, transition to plunge. Things get quicker because you are like getting closer, closer, closer to the plunge. So when here you use like what's called post-adiabatic expansion, like adiabatic, post-adiabatic effect. Here you have like it's post-leading transition to plunge, PLT, another type of expansion. Do I remember what PG stands for? But this is like when you have a plunge. Thing gets so quick, and here this quantity like is a slow variable, here become fast. You do another type of expansion. If you have to remember something, remember this cool plot here. The spiral overlies part with very early, we have one expansion. Transition to plunge, another perturbation, near geodesic plunge, another type of perturbation. You stitch them together, you compare like in a different regime, you match them in the regime which the expansion are both valid, and then you stitch the waveform all together. When you have perturbation theory, you have no source, you can get the quasi-normal frequency, the ring down. If you have like a source for plunging body, you have an emerger ring down. All right, what do we get? We get this beauty here. This is like a waveform which has been made by these guys here. It's like a self-force waveform. Remember, a waveform has been designed like to model memories. Big black hole, small black hole. Use like to model like binaries when you have like two black holes or roughly equal size. And what you do, like you stitch together a spiral, transition to plunge, and plunge, and you compare it with another waveform. Looks good. It looks good. Like I don't know about you, like it's looks good. Okay, but in this work we're doing also more sophisticated like comparison, like mismatches, doing things properly. This is just something I want to show you. There are some caveats which are considered a non-spinning binary, but a remnant is spinning. So how we do like with the comparison? It still holds? Depends. If you have like a simulation where the remnant is non-spinning, it's fine. If the remnant is spinning, you have some mismatch. It's just because like we are modeling a spinning binary all through the end, we make a simulation. That this can be adjusted like by considering appropriate, while doing appropriate comparison. They also have a sort of mismatch. I do like to mismatch it to the inspiral part. Also, like in fact, we're using like not enough expansion, like just that track. We don't have enough term here. We have just stop at 2. We have to write up to 7. I remember correctly. We can do some improvements, considering like a hybrid waveform. Why using just one approximation when we use 2? We take the best of the 2 approximation. As I also mentioned at the beginning, approximation like tossed between each other, and you have like what's it called, EN formation, like two like objects slowly moving to be in above the common center of mass, moving very slowly, very far away. It's like PN expansion. And their terms are valid to any order of the mass ratio, but they contain like approximation that take into account the motion up slowly. When you have like self-force term, with the expansion like in with a symmetric mass ratio, they contain all terms self-force, but in the all PN terms, but they only contains some information in symmetric. If you combine them, you take the best of the two, and you can have some extra information here that you don't have for this expansion, vice versa. And you can obtain like an approximation of an extremely complicated second order self-force by using like PN expansion. Then you have the evolution like total mass, the symmetric mass, the frequency, speed of the primary, and so on.
So what did the colors mean?
So I'm not sure. I think probably the size of the contribution, I guess. I'm not sure. Probably, I don't know if it's like was here. I don't know the color, I don't know if it's probably the size. I took the picture and said this is cool. All right, we're almost at the end. We are at the end. We get this beauty here. There's like a comparison between like this type of simulation. This is like your hybrid waveform model. It's still not good like for going to the last part, but we can consider like spinning the primary with the spinning. This is like for this mass ratio here. This is like astonishing because you have like a scheme designed for a completely different type of binaries applied to comparable binaries, to LIGO or sources. You show this, if you say this like probably 20 years ago, some people may say like you're nuts, so people say like makes sense, but here you have your result, and the last one just to show for higher like mass ratio, you have like, okay. And these two approach with the hybrid, the one that I showed before, can be combined to find a way to model like spinning binaries for comparable sources from self-force perturbation theory. Well, I'll end here. I don't know how much time do we have. A lot.
About 10 minutes.
10 minutes. Damn, it was too fast. I was afraid that like, I didn't have enough time. Damn. All right. If there are no questions, please.
Ask a question.
Sure.
So yeah, you showed that there were some results that these self-force results reach surprisingly far into the NR regime, right?
Mm-hmm.
So like I work in SXS, we do these simulations. I wonder, in your opinion, how far do you think we need to go into the high mass ratio regime to be sufficiently accurate for LISA and to do all the data? So how far do you think we need to extend our NR catalogs into high mass ratios to do everything we need to do?
That's an excellent question.
No one knows probably at the moment. But,
to have NR simulation like for cover all LISA sources, want to do mass ratio like using Q like 10 to the 5, 10 to the 6. Like it sounds crazy, but I think there was some work like to find some approximations. Like this is probably numerical relativity.
Yeah. Even when Nico Wittek.
Yeah, I think there's also a Libre. Yeah. It's with the problem of having like the right resolution, like you have different small body at a computer scale. I remember like there's this method like you have some analytic approximation like around the big black hole, and so avoid to not have all the resolution like And in principle, yeah, you have to go to 10 to a 5. Also depends the type of binaries that you want to model, because easily you have like many types. You are still also.
But I mean, at some point we can sort of rely on the self-force community to get these results and produce these waveforms, and then we only have to match up with the self-force community, right? But the question is, at what mass ratio can we sort of match up, right? Is it 10 or is it 1,000 or somewhere in between, right?
For your side, like the higher the better. But it's better like to have resolution like
we're trying, yeah.
No, but it's better like I think to have like small like is you have few waveforms or like
very high mass ratio.
A mass ratio is like not 2.5. I'm saying number like 128, like which are reliable.
Yeah.
Better like few simulation reliable,
yes.
different scale and so on.
Yes.
Instead of pushing like, and then you say, can we trust like the waveforms like
yes. Okay. Okay, we're trying. Okay.
Yeah. But there are like some also other effects like it's really nice to have, but also for comparison, we have been like for eccentricity, for instance, like adding like small eccentricity, have like also simulation like which have I think that for simulation when you have like signals which are like longer, probably it's nice to have like some hybrid with PM. It gives like a nice approximation. Something like interesting to have simulation with eccentricity. That is something like it's really
at high mass ratios.
The one which you can get like accurate waveform, like it's doesn't matter like it's high, like it's like 4, 2, like that. Just add eccentricity, like some sort of.
Yeah, we're doing that. Absolutely.
I'm not judging you, like it's also like.
Yeah, eccentricity is not as much of a problem as the high mass ratios.
The problem is more like how to do comparisons. That's how you define eccentricity and how do you extract eccentricity. Also, there's also because I watched some of the talk, even like these consortium, like also high spin, like it's spin like larger than 0.9 is also a problem, like for the microsimulations. If you go to the like form limit like a equal 0.998, like when you have like I remember like the maximum spin that you can have from a equation, like this I think is very difficult to get like from. I don't know, I am asking like I know.
Yeah, I think there are some extreme spin simulations that we've but yeah, most go to like 0.85 or so. But yeah, I think these are
well, I guess something slightly different, but related to what both of us have been working on. What about secondary spin in some of the like hybrid waveforms that you were talking about? Is this something you've thought about?
Something will be.
Seems like a natural thing for you to work on next.
Question. No, I wanted to show some a slide. It was some work done by Josh Matthews. Like it's something that can be done. For spin align, we are working together to like spinning binaries with both spin align. And from a spin sector, like for rocket, it's relatively easy. Like just get the fluxes, everything that you get from memories, and just use it like that. Everything is clear. The problem is when you have possession, because you have to, how do you compare, like, I think it was a problem with frames, like, right. So how to compare, like, people in self-force don't know which frames are. You have to compare, like, numerical relativity, they know how things are complex, how do you compare that? The sense is, things can be produced like easily, from our side. The problem is how to compare like properly. The spin align fine, you can easily possession is to produce, but not easy to compare.
Just one question.
Hmm?
So in the very final waveform you showed, it didn't have the ring down?
Yeah, it doesn't have the ring down.
Like in the earlier versions it did.
Yeah,
So
because
is this
this.
something you're working on to make the ring down part more accurate?
Yeah,
I know you mentioned there were issues with like the skin of the remnant stuff.
yeah, it's basically like because we.
Right, because it's not spinning. Yeah, because the amplitude of the ring down is not great there.
Yeah, because it's you will consider like they're considered as non-spinning binary.
Yeah.
So this is something we're also working to try to add the both spin. Something it's a work in progress because it's you need to solve for the source, and that is complicated. Like it's not easy task.
Is the issue matching the end of transition or the end of the plunge with the ring down? Or?
I have to be honest, I don't know how difficult like to do the matching. Yeah, I guess to the matching shouldn't be too difficult. The problem is to have things done properly here and here. This is fine. This is something like yeah, here like the related to the source, having like compute like the source for a plunging particle. Also here having like enough terms.
And so like going from that waveform to one you showed at the end, did they add more terms in the transition to plunge and that's why it looks
No,
they still need to add more.
We still need to add more.
I think one looked better because the remnant was not spinning.
Yeah.
The one on the left.
Yeah, gotcha.
How much time do we have? I have also extra slides to show. I can briefly comment on that.
Yeah, we have about a little bit more than 10 minutes. So if anyone else have questions before the bonus slides.
Maybe I have a naive question.
Sure. There are no naive questions.
No, next question. So, how is it possible? Because your perturbative expansion is on the mass ratio, no? So it's 1 over q. You are showing a result with q equal to 10. So that is not a 1 over 10, it's not a small parameter that you can expand with. How is it possible that there are no differences with the NR simulation?
There's also a mapping.
Now I use like this epsilon, which is like 1 over q. Epsilon like is the small mass ratio, q like is the big one. Your question is like how it's possible that
because in the former slide, again, maybe it's naive, but
this one?
Yeah, this one. I said there is perfect overlap in the spiral of the NR. But you're doing a post-adiabatic expansion. So this is a 1 over q expansion. And if q is 10, 1 over 10 is not a small number that justify a perturbative expansion. How is it possible that there are no differences with the NR?
There must have been a q equivalent.
This is no, in that case, they also do a post-Newtonian expansion. Maybe the post-Newtonian compensates for something.
Anyway, you go.
This is an excellent question. Like I asked the same thing because there was Tokowski said to me like, show me the presentation like in advance because I'm not be able to see it. He asked me like, how is it possible that you can have this? And Tokowski, so he told me like, well, it may not be surprising. Like the thing I remember it's because when you go, things are complicated from the source. What's happening in the source, things are complicated. When you go very, very far away, some of the complicated details are just mirrored out. So things, when you will see things away, looks much more easy like what's happening.
But still, the only parameter of the expansion in the spiral here is 1 over q, right? And 1 over q is big.
It's
1 over 10 is big.
No, it's a matter of some people. Well, it depends how you do your Taylor series. Like for some people, like 1 over q, like 0.1 is more. For others, like I agree. The only thing is that I can say
there is no difference that I can see by eye. I'm not surprised.
That is the whole point,
There's some-
like, I mean, this is why people are interested in using perturbation theory.
But that means we don't need any more an art simulation.
That's what I just
that's
what I just asked.
No.
How far do we need to go?
Let me be clear.
So that
This,
Yeah, thanks.
this is like NR of all the methods that I showed you before. NR is the only one that takes the full Einstein field equation and solve numerically. The approximation gives that the numerics, but there are no small parameters and so on. They are the gold standard. It's something, so you need simulation, you need good simulation. As I said before, you can have all the fancy model that you get, but if the mismatch was like use this model, like you just really go here, just go like, so it's useless. We need NR simulation. It's something to calibrate, say like this model like works for this parameter.
But we're definitely currently trying to figure out to what mass ratio we actually need to go. If maybe our current curvature of pupil 10 is enough. It's not because we need high mass ratio simulations to actually validate these models as well, right? And see if they actually valid at least a few. But yeah, it's an open question at the moment. And also, I don't think anyone really understands why self-force extends into the comparable mass regime so well.
So this is not understood.
No, it's also relatively recent. In the last few years, this has been a bigger.
This is like that perturbation theory works in a non-linear shape.
Yeah.
But here, it's but here like it's pretty linear.
Waveform.
Yeah, here it's still linear. It's when you go like to a merger, like the things are proper, you know. But yeah, it's something that is not. For some people, I asked the course, they say like, oh, this is fun. It's the same for. But you're right. It's not something that is properly like.
But I think people were already surprised when they got the first full in-spiral merger ring-down simulations because they look so simple, right? Yeah. So it's kind of the same thing.
Well, actually, I mean, sure that's this is like this taken by form paper like this sketch of the waveform like in his original sketch was like when you have here, so like all these type of things happen and it's not very clear. I want to say like it's surprising that you get something this simple.
Another estimation of the phase error of the self-force waveform in terms of move or number of orbits?
In the sense of how compared to this, I'm not sure for the binaries that you need to model. This is like the type of error, like this is like your phase, orbital phase, and this is like the order that you need to get. So if you have the rule of thumb that you have like the thing, if your waveform is out of phase of 2 cycles, like 2 orbits, you may have an effect which is detectable by laser. So you have to get better, like you have a model which needs to have errors like less than 2 phase cycles. Over a year, yeah. That's the crazy levels. This is why there's a lot of work like this, and also when you also like a thing that when you have my mathematics, you have my nice time domain waveform. Like okay, I need to sample, and you really feel like over 1 year long, like you say, like how many points do I need? Like a million. Oh. And then you just wait like UV-FFT and UV transform. But yeah, it's a few cycles, like 2 or 3 cycles. A few. There's like rule of thumb is 1 radian, but it's.
I think if you have like a longer discussion questions, you can also schedule to meet with Gabriel as well. Like there are 2 or 3 open spots for today. So I think we have Maybe we can give us like a 5-minute sneak peek into your bonus slides.
Oh yeah, yeah. It's. I hope I didn't watch too much in there on the previous part. I was worried like it's too much info like dump into. But okay, I want to show this. I'm happy that I. Probably I can show resonances, but I want to show like no, resonances. Not that boring. They're cool. But I want to show like this, like some actually. This is fine. This is a work we did done like with Oliver. We did all the data analysis. Did some like estimate. Like this is like some data analysis that for Emory with the model like if you have the complete 1 p.m. model, circular, equatorial orbit with partial, but we have all the surf-force data between. And we have, the question is like, what's happened when we neglect some of these terms? We have like 0 PA, so no surf-force, no small speed, some approximate model and so on. This is like the full effects that we have. And the bias that you have when you neglect these things, that this is like the inject value, are like tiny. You ask for an astrophysics point of view, like you can model everything with this, you are totally fine. You know what I mean? Cell force, lobes, like if you are happy like with 1%, 10% error, like the mass of a big object, why you need like all of this? The reason like for doing like test of general relativity, if you want to see if there are over effects happening in the binary, if you have like scalar fields and so on, these effects become like important. This is like for mass ratio 10 to the minus 5, things get like this, 10 to the minus 4, they become worse. Like your model like have like significant important bias. If you go for even higher mass ratio, I think you get even worse. You can get some nice results with this approximate model, but yeah, it's okay. Again, astrophysics, they are perfect. Test of GR, not so well.
How much SNR do you lose?
Personally, I don't remember. Like probably for, I think for detection, this should be like still good, still good enough. It's more about of. It's a good, excellent question. It's more about the biases. There's another thing you see like SNR, which is relatively high. To like to 20 in these biases like this way. Now I think that okay, it's like the full like contour and triangular plot done by Ollie. Was really proud like to show this with all the parameter and all the things like, well, can we measure the spin of a small body for circular equatorial orbits? No.
No.
You have like this distribution here, it's flat. You know, cannot get anything there. What's happened like get a little bit better, but I also think other things to show here is like you have these tails here. This is like your distribution is not Gaussian anymore. This is like some correlation in the spin.
Sorry, I missed the difference between, what did you change between the first and second?
It's the mass ratio.
Oh, mass ratio.
Yeah, this for larger mass ratio, you can kind of measure the spin, and you have still some. You have less and less like tails. These are like here all the angles. These are like the positioning, the scan. These are not. This was the story up to beginning of this year. There was a paper recent, like I don't have slides. The Yao Channel, sorry if I mispronounced. We did like a full. It is like an analysis, like for the try to measure the spin of a small body for genetic orbits. Their work has several caveats. Fisher matrices, mixed Fisher matrices, approximate wave variables like clouds, like just P and M. But it seems that for generic orbits you can measure the secondary spin. And I think if you use proper waveform, like the estimate is like about 10%, I think you can get even better results. In that paper, the interesting thing they show that if you can measure the secondary spin, you can have some ideas like for the formation channel, like white memory, white over different channels. And what the analysis of the fact that you use Fisher, in a Fisher matrix, what you do, like you assume that your probability distribution is a Gaussian, a nice bell shape. What you have here, you have these tails. This is like not Gaussian, like it's not Gaussian at all. So this is also like circular equatorial orbits, extremely constrained. Like,
Could you not do eccentric 0 PA plus spin?
it can be done, yeah. It's something that I think it was Victor Scoopy and Lorenzo Spey has been working on this.
Okay.
People would like to work on also for spherical orbits. But yeah, it's a question, something we are working on.
One of the issues there is that you don't have the high order self-force terms, but yeah, so.
Yeah,
Yeah, but
but
we can
it
sort of
seems
obviously,
that
Yeah, you know,
PA is
yeah, I agree.
enough
It should be done, yeah.
to get a sense. And
Oh, yeah, no,
You need to plug everything like into few and then like Pascal Lorenzo, like Lorenzo, please, or all the.
He's working on it, but yeah.
Lorenzo Spey is working on so many also. It can be done. We are working on this. Okay, this is very and credits. These are just a list of nice review, not a review, but points, nice pointers like white papers. I can share these slides, but they are on YouTube, so now I'm on YouTube forever. And, there's some nice things. What every fast and waveform use few. In here, exact, I use it a lot. It's difficult to use, but it gives you satisfaction. The toolkit. One-to-one perturbation theory, use the toolkit. And then I shut up.
So we are unfortunately